Hello everybody, getting ready to do lesson chapter 7, review and summary for pre-calculus math today, part 1 of your classwork lesson. My email is animatedpowerpointmathvideo@aol.com if you need class worksheets, homework sheets, etc. And for today's lesson, part 1, chapter 7 summary, you got 12 points here to go into your notebook guide. You got 50 points here that will go on to your classwork sheet. Students, please put your name and date. If you're in my classroom, put your period. If you're online, put your due date in here. And then page 1 today is our bell work. For today's lesson, we have a bell work here. Determine whether the statement is true or false. Justify your answer. So, solving a system of equations graphically will always give an exact solution and say true or false, and then justify your answer here. For 195, for this one here, justify your answer there for that one on your bell work. Okay, welcome back, students, after your 5 minutes of doing your bell work for today. For 194, solving a system of equations graphically will always give an exact solution. So for false, the solution may have irrational numbers. You may have an imaginary number if you have a graphing calculator that can do that. So the solution may have irrational numbers. That wouldn't be technically, it would not be an exact solution. And then for this here, is this true or false? Determine whether the statement is true or false equals this here. So the expansion by row 3 gives, the row 3 expansion will give us this gnarly lesson here. So our row 3 here will give us this here, A31 plus C1. And then we have a negative A12 plus C2 here. So we're going to use our formula here for finding a determinant for a system of equations. And then when we do that, we come up with this solution down here, which will give us this. Note, expand each of these matrices by row 3 to see the previous step. So that is kind of a difficult bell work there, but at least you see the solution to expanding your row 3 here. You come up with this abstractions here. That explains what you actually do with actual coefficient matrix there. Okay, into our first page here of our 7.1 for our review and summary. What did you learn in 7.1? Use the methods of substitution and graphing to solve systems of equations in two variables, and use systems of equations to model and solve real-life problems. So that's what we had in 7.1. So an example of that, explanation and examples. Substitution: 1, solve one of the equations for one variable. 2, substitute that expression found in step 1 into the other equation to obtain an equation in one variable. And 3, to solve the equation. 4, back substitute the values obtained in step 3 into the expression obtained in step 1 to find the values of the other variable. 5, check the solutions, or by graphing, solve both equations for y in terms of x. And then 2, use a graphing calculator to graph both equations. 3, use the intersect feature or to zoom and trace features of the graphing utility to approximate the points of intersection of the graph. 4, check the solution. So that'd be the way that you could do it, by doing graphing. Okay, let's try an example now of these types of methods. Solve a system of equations graphically. In exercises 11 through 18, use a graphing calculator to approximate all points of intersection of the graphs of the equations in the system. Verify your solutions by checking them in the original system. So for this situation here, here's our solution there. There's our point of intersection. There'll be a 4, 4 there. By using trace, you find out that your intersection will be there, or the intersect feature of your graphing calculator. For this system here, your solution will be a 4, 4. So when x equals 4, y equals 4. So 4 minus 2 would be 2. 2 squared equals 4. Yeah, that checks. And then for 18, y equals natural log x plus 2 plus 1. And then this system here, x plus y equals 0. When we graph that, here's a point of intersection there. It'll be negative 1, 1. So that would be kind of the methods that you would use that you found in 7.1. So let's try one now. Use a graphing calculator to approximate all points of intersection of the graphs of the equations in this system. So we have this system here, and down here, students, we have this system here. Verify your solutions by checking them in the original system. So we have this system here, and if we go ahead and we use our graphing calculator, we'll come up with these points of intersection here. This is quadratic, so that's why we'll have two solutions for that one. And then here's your graph here. You have a solution there and a solution there for this system here. And then down here, you have two quadratics. Okay, so getting into our next section here, 7.2. What did you learn in 7.2? Use the method of elimination to solve systems of linear equations in two variables, and graphically interpret the number of solutions of a system of linear equations in two variables. Elimination, so methods here of doing this will be 1, obtain coefficients for x or y that differ only in sign by multiplying all terms of one or both equations by suitably chosen constants. 2, add the equations to eliminate one variable and solve the resulting equation. 3, back substitute the value obtained in step 2 into either of the original equations and solve for the other variable. 4, check the solutions. Explanation and examples. Elimination 1. Obtain coefficients for x or y that differ only in sign by multiplying all terms of one or both equations by suitably chosen constants. 2. Add the equations to eliminate one variable and solve the resulting equation. 3. Back substitute the value obtained in step 2 into either of the original equations and solve for the other variable. 4. Check the solutions. So let's try one here. Solving a system by elimination. Solve the system by method of elimination. So here's a system here. And then your independent down here, students, use a graphing calculator to graph the lines in the system. Use the graphs to determine whether the system is consistent or inconsistent. If the system is consistent, determine the solution. Verify your results algebraically. Okay, so back up here. For this one here, we can go over here. We can multiply through by -1. And then we can add here, and we end up with these cancel. Then this equals x equals -3. And then when we plug that back in up here, you get y equals 7. So that'd be a fast way of solving the system here. X equals -3, y would equal 7 for that one. And then this is your independent practice here, students, so proceed to do that. 7.3, what did you learn in 7.3? Solve non-square systems of linear equations. 7.3, explanation and examples. So for 7.3, in a non-square system, the number of equations differs from the number of variables. A system of linear equations cannot have a unique solution unless there are at least as many equations as there are variables. So like for example, this one here, we have a 2 by 3 here. So we have 3 variables and we have 3 rows. It's not a square. It's not a square system. Solve the system of linear equations and check any solution algebraically. So to solve this one here, 3 times equation 1 and -5 times equation 2 will give us this. These will cancel. And then when you combine these two, you come up with a -y. And then these here will come up with a positive z. And then this will be positive 3. So when you do that, you end up with this situation here. And then you just go ahead and you solve for your variables once you know that. So adding -y plus z equals 3, this will become y equals z minus 3. And then you plug that back into the remaining system, and you crank all this stuff out, and you get x equals z minus 4. So let z equal a, then x equals a minus 4, and y equals a minus 3. This is what you have to do when you have a non-square system. So the answer would be a minus 4, a minus 3, and then a, where a is any real number for x, y, and z. So x would be a minus 4, which would be z, and then y would be a minus 3, and then a would be z in that case. And then this one here this is your independent practice here, students. So go ahead and give a shot at it from your guided practice. And also from your classwork sheets or homework sheets, you should pretty much be able to knock that out, no problem. Okay, moving on now to our next section here, 7.4. Use matrices and Gauss-Jordan elimination to solve systems of linear equations. Gauss-Jordan elimination continues the reduction process on a matrix in row echelon form into a reduced row echelon form is obtained. So in exercises here, use matrices to solve a system of equations if possible. Use Gauss-Jordan elimination. So we do have a 3 by 3 here. So this would be our A here. This would be our enhanced form here. This would be a coefficient matrix here. And then when we multiply row 1 by -1, we get this. And then 2 times our row 1 plus R2, we get this. And then 5 times row 1 plus R3. So we're starting to get our row echelon form here. And then we go 1/5 times row 2, and we end up with this here. And then we multiply row 2 plus row 1. Rather we combine row 2 plus row 1. And see row 2 plus row 1 here. Row 2, okay, here we go. Row 2 plus row 1. This will go away. And then this becomes -1. So we're getting there closer. Then -9 times row 2 plus row 3. So this will go away. So now we have this 3 equals 9 here. Once we have that, excuse me. And then 1/3 of row 3 will give us, so z will equal 3. And then we go row 3 plus row 1. This will go away. This will give us this. So x equals 2. Then a y. Negative row 3 plus row 2. Negative row 3 plus row 2. So we put this up here like that. So now we get our y equals -3. So now here's our solutions there by doing it that way. Answer is 2, -3, and 3 for that system there. And then for this one here, use matrices to solve this system. Here we got a 3 by 3. Then use Gauss-Jordan elimination. So here's our coefficient matrix. And I'm going to let you do the rest of it, students, okay? And that is your lesson part 1 of Chapter 7, Review and Summary, Pre-Calculus Math. And if you need solution PowerPoints, class worksheets, homework sheets, note-taking guides, email me at animatedpowerpointmathvideo@aol.com. Thank you very much.